There we go. All right. So before we get started, any questions about the final exam? Questions? It is longer, okay? It's 105 minutes instead of 70 minutes that our midterms are. So that means there are more questions. It is cumulative. I would say it covers all material equally. The new chapters covered on the final are chapters 23 and 21, so transition metal chemistry and nuclear chemistry, and those are rather shorter chapters. So like don't expect like 10 questions for each of those chapters. They're going to be rather smaller because they're smaller chapters, and then the rest of the exam will just cover the other chapters equally. All right, okay. So this packet is set up into two, I'm recording, right? Yes, recording. Two parts, so the new chapter material, so 23 and 21. So since that's new material, let's just start there. So I'm not even gonna give you the option, let's just start there. To go over the new material, and then we'll go review some older material, you know, midterm practice material that we covered in midterm 1, 2, and 3. Okay, let's get started. Okay, so at least for my class, oh, you don't want my face and my name. No. Okay, just put you in the corner. There you go. All right. So transition metals, they get their own chapter because they're weird. In 1210, we saw that transition metals are a lot of the exceptions, especially when it came to electron configurations and all of that. So we kind of explored the interesting phenomena that specifically happens with transition metals because of their low energy d electrons. Some weird stuff happens. So let's just quickly review how to write electron configurations. So here I have some iron species. You know, this is a 1210 question. What is the electron configuration of just straight up iron? This is, yes, I see eyes darting to the periodic table. Very good. So we have argon. Then potassium starts what group? It's an S block, but which S? 4s, very good. 4s2, and then next scantium all the way to iron. That would be 3d, 1, 2, 3, 4, 5, 6 electrons. There we go. Okay, so that's our neutral iron atom. But now to make the cation versions of these, we need to start removing electrons. So I need to remove 2 electrons from my neutral iron to make iron 2+, but what's the trick here? What electrons do I want to remove? S before D. Yes, you always want to remove S electrons before D electrons, and some students are kind of weary about that because they're like, well, I put the D electrons last. Shouldn't they come off first? So the way that we do electron configurations is kind of fake. It's just a way to get to the answer. Atoms don't actually form that way, you know, putting electrons in one at a time. So the order that we remove them is not the same order that we place them. The real answer here is we remove the highest energy electrons, and those happen to be in the 4s orbital. So even if we were talking about like ruthenium, right, which is one group down or one period down, we would again remove S electrons before D. So we see that iron 2+ will be argon 3d6 because we're removing those S electrons. And now to make iron 3+, we need to remove an additional electron. There's only one place we can remove it from, so it's going to be argon 3d5. Is there anything special about a d5 electron configuration? It's stable. Why? They all are spinning the same direction. This is an example of this enhanced stability of a half-filled subshell. All of them are dancing in the same direction, and that is unreasonably, or I guess surprisingly stable. And so we see that iron 3+, we don't get higher oxidation states for iron 3+. This is the most stable oxidation state of iron. When we think about like iron in our world, we think of things like iron 3 oxide rust. It's the most common form of iron, and we see that from the electron configuration. D5, very enhanced stability, So that's what we see in nature. Okay, great. Okay, so yeah, big thing there, S before D. All right, so question 2, which of these substances is predicted to respond the most to an external magnetic field? What is this question asking? What's it asking? What types of things respond to magnetic fields? Yeah. Whether it's paramagnetic or diamagnetic. So which one of those will respond to a magnetic field? Para. Yeah, so essentially this question is asking electron configuration again. So really no different than question 1, but the difference here is that I didn't straight up give you the oxidation states of the metal. So that's what we want to be focusing on here, is what is the electron configuration, oxidation states for the metals shown here. We have to write their electron diagrams and then interpret their electron diagrams to see are they para or diamagnetic. So let's just do all of them at once. So the first idea here is get the oxidation state, all right? Basically the charge. What are the charge of these metals? So iron sulfate, what's the charge of that iron? It's iron what? 2+, yes. Nickel? Also 2+. Cobalt? Also 2+. Whoops, I didn't put a 2 there. And manganese? Also 2+. So all of these have 2+ oxidation states, but we need to go one step further and actually get their electron configurations. All right, so iron 2+, we are losing 2 electrons from their neutral state. So do we know what electrons we're going to lose first? For those? Yeah, they're going to be the s electrons. So we're basically just looking at what are the leftover d electrons for all of these, because they're all +2 state. If it was a different charge, go through all the steps like we did for number 1. So iron is d6, nickel is d8, cobalt is d7, and manganese is d5. Great. So the superscript tells us how many electrons there are, so we just have to draw the electron diagrams to see, are they para or diamagnetic. So iron 2+ has 6 electrons, there's 5, the 6th one becomes spin down. So is this iron 2+ paramagnetic? Yes, it is, because there's unpaired electrons. So it will respond to a magnetic field, but this question is responds the most to a magnetic field. So what are we looking for? Not only is it paramagnetic, but also which one has the most unpaired electrons. So hopefully you can see, without drawing all of these, that nickel 2+ is going to have how many unpaired electrons? I guess 2 unpaired. I don't feel like drawing it. All right, so you fill up 5, you add 3 more, those become paired, so there's 2 unpaired. Cobalt is going to have 3 unpaired, and then manganese is going to have 5 unpaired. And I'll draw that one because that's our correct answer. Oh, but not enough orbitals. 1, 2, 3, 4. 1, 2, 3, 4, 5. So you see 5 unpaired electrons, so our answer is manganese. So this question number 2, a lot more likely to be an exam question versus number 1. 1 just kind of set us up for it, because in question 2, you have to do all the things in question 1, but you have to do it 4 times, all right? And recognize what type of, are types of magnetism here, para versus diamagnetic, and those properties. All right, so there we go. Next one, which of the neutral atoms, so order them in increasing melting point temperature. So with these, melting point temperature, this trends with size, all right? So as size decreases, these are all metals. We typically see metallic bonding increase when size is small. So, just kind of thinking about this, when we melt a substance, we're breaking those metallic bonds. So typically we'll see our melting point temperature increases as metallic bonding increases or as size decreases. So if we look at, scantium, iron, and yttrium, scantium, this is a 3D element. It's 3D1, iron is 3D6, and yttrium is 4D1. So of these, do we know which one's the biggest atom? Yttrium, yeah, because it's 4D, all right? So yttrium is going to have what, the highest or lowest melting point? Lowest, so it's going to be yttrium first, all right, in terms of lowest melting point. And now to get the other ones, we need to recognize the trends in size across the D block, which is weird. In 1210, we talked about size typically decreasing as you go across a group, all right, because of the increased Z effective nuclear charge. So for example, when we compare sodium and magnesium, they're right next to each other. Magnesium is actually smaller, even though it's a heavier atom. And the reasoning is because Z effective increases as we go left to right across the periodic table. So when we look at the transition metals specifically, because there's so many electrons there, what we actually see in terms of size is that it decreases initially until we kind of hit the halfway point. And this is, again, because of Z effective. But as we approach like our D10 transition metals, we see size start to increase again. And the reasoning is like once we get to copper and zinc, you're shoving 10 electrons in a small space. Electrons are negatively charged. Things that are negatively charged repel one another. And because we're trying to put so many electrons, 10 electrons in that small space, we see electron repulsion start to take over towards the end of the block. So this is E repulsion. All right, so based upon that, which is smaller, scantium or iron? Iron is smaller, so it's going to have the highest melting point, and then scantium is in the middle. There we go. So the idea here, scantium is smaller than yttrium because of the N value. So N equals, 4 here, N equals 3 for those D electrons, and then iron is smaller than scantium because of the effective nuclear charge. Okay, so there we go. That is size, and so it kind of asks both, size in terms of transition metals, and then relating that to melting point. Okay, great. All right, let's keep going. All right, so kind of the cool things that happen with transition metal chemistry is we get these complexes. Complexes, we already learned kind of about them a little bit in chapter 17 when we talked about KF. KF is typically a really, really large equilibrium constant. It's the formation of a complex. And typically these complexes are soluble in water. So that was, one of the ways we increased solubility of certain solids. We increased their solubility, but we didn't change KSP solubility product. What we did instead was form this new complex. So in this chapter, we kind of explored this more deeply and looked at the structure of transition metal complexes. So this question is asking, what is the oxidation state? So essentially, this is asking, what is the charge of the metal, the transition metal? And then what is the coordination number around that metal? So coordination number, it's not necessarily the number of ligands, it's the number of bonds directly to that metal. And it becomes way more apparent when you actually see the structure of it, like how many bonds are directly bonded to that transition metal thing. So let's kind of do the easy ones first here, and that's getting oxidation state or the charge of those metals. And so the idea here is I would just memorize some of the common ligand charges, and that will help you figure out, well, what does the metal have to be in order to be, charge balanced. So when we think about ammonia, what charge is ammonia? Or is it charged? No, it's neutral. So ammonia is an example of a neutral charged ligand. So if there's two things attached, two ammonias attached to that silver, what is the charge of that silver? Silver plus, that's it, all right? There's two neutral things shoved on it. We see that the whole complex is plus charge, so silver has to be plus. So its oxidation state or number is 1. All right, so what is its coordination number? Again, not necessarily number of ligands, but it's the number of things bonded to it, or the number of bonds to it. So we see there's 2 ammonias, so the coordination number here is 2. Yes, all right. Okay, so let's do the next one. We have ammonia again. So those ammonias are charge neutral, but it looks like there's some chlorides attached there. Chlorides typically, you know, when they're in ionic compounds, what are their charge? -1. Whoops, sorry. -1. Where am I? Okay. So chloride is an example of something that's -1. So do recognize to take inventory of that charge. Other halides like bromide or fluoride also have a charged, are charged typically in species like that. So if chloride is -1, there are 3 chlorides, all right? So there's a total of a -3 coming from those chlorides. So the complex itself is a total +3 charge, all right? So what does the charge of cobalt have to be? +3, yeah, because there's neutral ammonias there. And so again, take inventory of all the charges, you know, like this was chapter 2 in 1210 or whatever. Take inventory of those charges to figure out what that transition metal charge is. All right, so what is the coordination number here? What is it? 6? Well, why not? Why isn't it 9? There's 3 chlorides there too. They don't count. Why don't they count? They're not actually bonded to the complex. Those chlorides are there, why? To stabilize it, to make it charge neutral. You can't just grab a cation off the shelf, all right? You always grab it as a neutral salt. So those chlorides are there to make it charge neutral. That's the only purpose. We can also say those chlorides are in the outer sphere versus the inner sphere is the coordination sphere. So the thing's actually bonded to cobalt. So this is 6. All right. So the next one, cobalt En3. What does En stand for? It stands for ethylene diamine. Yes. So ethylene diamine is another example of a neutral charged ligand. I like to think of ethylene diamine as 2 ammonias just tethered together. All right, 2 ammonias tethered together. So ethylene diamine is also neutral, though these would be H2, but whatever, it's 2 ammonias tethered together. So same idea here, 3 chlorides, ethylene diamine is charge neutral, so cobalt is 3+. What is the coordination number here? Is it 3? No, it is also 6. So cobalt En, ethylene diamine, is again 2 ammonias tethered together where each sides of that ethylene diamine, so maybe I'll draw it. I think it looks like this, all right? 2 hydrogens, okay, with a lone pair. Each of those lone pairs can bond, make a coordinate covalent bond to that metal. So 1 ethylene diamine bonds twice. What do we call that? Bidentate. So bi means 2, dentate means bite. Yes, so it bites twice. That's ethylene diamine. So things to know with ethylene diamine, I would just say memorize it. It's charge neutral. It bites twice. It's a bidentate. I would just memorize that. Because we have ethylene diamine, other bidentates are bipi. So it's bipyridine. Is another example of a bidentate, and what's another one? Oxalate, so typically it is abbreviated OX. This does have a charge that's 2-, but both of those are bidentates as well. And so that will affect your coordination number that you calculate. All right, okay, so now this other one. Okay, so now we have some mixed up things going on. So we have cobalt, 2 ethylene diamines, chloride, and bromide. All right, can someone tell me what is the charge of cobalt? +3 again, yes, because there's 2 chlorides, 1 bromide, that's -3, ethylene diamine is 0, so cobalt has to be +3. So what is the coordination number here? 6 again, yeah, because 2 ethylene diamine, so bites twice, that's 4 coordination numbers, plus 2 more chlorides, that makes 6. But what about the bromide? Do we count that in the coordination number? No, because it's on the outside. Great. For funsies, what is the charge of the whole complex? What does it have to be? +1, yeah, it does. Okay, good. And again, the reason that bromide's there is just to make everything charge neutral. Okay, great. Okay, let's keep going. Oh, blank page. All right. What about this one? So let's, what's the charge of this entire complex? +2, yeah, because nitrates are -1, so that's -2. All right, so what does that cobalt have to be? +3 again, great. Because bromide is -1, all right, with -2 coming from nitrates, cobalt has to be +3 because ammonias are charge neutral. I did ammonia a lot. What are other charge neutral ligands? So we have ammonia is a common one. Water is also a common one. I guess ethylene diamine, Biffy. I can't think of any others. I don't know. Yeah, so those are charge neutral ligands. These two are monodentate, these two are bidentate, and then other charged ligands. So we saw chloride, bromide, cyanide is also a charged ligand. Thiocyanide is also a charged ligand. I don't think that's right. It's SCN. Are also charged ligands. Right, oxalate, which is a bidentate, is also a charged ligand. All right, okay. So I would just memorize those. All right, because when written in a complex, you can't really tell what the charges of those individual ligands are. All right, what's the coordination of that cobalt? 6, yes, it is 6. Don't count the nitrates. All right, so now this platinum compound, what's its charge? Platinum has to be +4, yeah, because there's 4 chlorides. What's its coordination number? 6 again. Yeah, octahedral coordination complexes, they're very common, very common. All right, let's keep going. And we see, to try to show what the complex is, see how those brackets are trying to say, hey, that whole thing is the complex. That whole platinum is in that octahedral coordination sphere. All right, so now we have this other thing. So we have this tin compound, all right, has some chlorides and some sodiums. Are the sodiums attached to the platinum? No, it's not, because they're not in the brackets. It's in the outer sphere. So the inner sphere is chlorides that are there. So what is the charge of the whole complex? It has to be -2, yeah. So we just need those sodiums there to understand, you know, the neutral ionic compound. So that means tin has to be what charge? +4. Yep, +4. And then what's its coordination number? 6. All right, potassium, there's 4 potassiums, so that means this whole complex has to be +4. So manganese is what charge? Yeah, so recall what the charge of cyanide is. Let me zoom out a little bit. What are our common charges? So chlorides, bromides are minus. Cyanide is also a minus charge. So you can just balance it like it was a chloride or something. There's a -6 coming from those 6 cyanides, so manganese has to be +2. And there's 6 things attached to it, so it is coordination number 6. Okay, great. All right. Shouldn't the charge, yes, it should be -6, I'm sorry. -6. -4, there we go. Yes, -4, because +4 is coming from potassiums, but my manganese 2+ is correct. Whoops. All right, so those are, you know, deducing charge coordination number from just the composition, just from the formula of the compound. So this next part is, okay, well, if I give you pictures of these complexes instead, can you deduce what kind of isomer you're looking at? Yeah. Oh, is it wrong? Probably. I write a lot of keys. Yes, I did write +4. Whoops. It is not +4, it's +2. All right, I'll fix it later. All right, so From these pictures, we should be able to deduce if the isomers that we're looking at, the types of isomers that we studied specifically within transition metal chemistry, have to do with being structurally different from one another or spatially different from one another. So again, isomer just means that the formulas are the exact same. So we have the exact same atoms in our chemical formula. It's just, okay, how are the atoms actually bonded to one another makes these isomers different from one another. So, you know, I always say the secret to chemistry is that composition and structure dictate chemical properties. So here in this chapter really highlights the importance of structure. Yes, we can have the same atoms present in a compound, but how they're actually bonded to one another is equally as important. So these are what we can choose from. The different types of isomers that we've studied is coordination sphere isomers and linkage isomers. These are examples of structural isomers where the actual bonds differ from one another. And then the last ones here, these are stereoisomers. All right, stereo meaning like space, like, you know, when you have like stereo surround sound like headphones or whatever, it differentiates left and right. That left and right have unique sound profiles to them. And so it's the same idea here. Stereoisomers have unique spatial requirements where how you arrange the actual bonds themselves differ. All right, so I guess going through these really quickly, coordination sphere isomers are when you swap what's on the outside sphere and the inner sphere. You just swap things on the inner and outer spheres. That's a coordination sphere isomer. A linkage isomer is where you have a ligand that can bond in different places. So an example could be like nitrite, right? If you drew the Lewis structure for nitrite, I think that's what it looks like. There's lone pairs on oxygen, so that oxygen can bond to the metal, or the nitrogen can bond to the metal. There's multiple places where it can bite. So that would be an example of a linkage isomer. Geometric isomers, we have two different kinds, cis and trans, Faish and Mer. We have optical isomers, so we're typically looking at mirror images. All right, and then my favorite is, okay, maybe I give you a mirror image of a molecule, but it actually is the same molecule. So only optical isomers where when you take the mirror image, you actually get a brand new unique molecule that has different optical properties. But sometimes when you take a mirror image of a molecule, you actually get the same molecule back. So understanding how these molecules look like in space, very, very important. And I asked my class, anyone here pre-dental? Anyone's pre-dental? Yeah, so the idea of mirror images in dentistry, really important, and spatial awareness, very important to dentists, because you're gonna spend the rest of your life looking through a mirror. Yes, so okay, so hopefully you can grasp this. All right, so what we see here are a lot of octahedral compounds. All right, so recall an octahedral compound, although this iron is drawn flat, it is not flat. An octahedral has 6 bonds to it, all right, where each of those bonds are 90 degrees from one another. All right, so I like to play the game, spot the difference between those two pictures, and then not only find the difference, but define what that difference is in terms of what kind of isomers are they. So let's spot the difference. How are these different? The ammonias are different, but I want to make it even simpler for me. It's the cyanides, they're different. Wait. Oh wait, no, you're right, it's the ammonias. Yes. Okay, yeah, the ammonias are different. I mean, yes, the cyanides are different, but there's 4. You're like taking track of 4 of them. So it's easier if you look and see, okay, how do the ammonias differ from one another? Because there's only 2 you're keeping track of. All right, so how do those differ? What kind of isomers are these? Cis and trans, yes, cis and trans. So in this example, ammonias are next to one another in the coordination sphere. And then in this compound, they are across from one another. So that's the trans version. Yes. So these are stereoisomers. They have the exact same chemical formula. If you count every atom, they're the exact same. It's just how they're arranged spatially are different. Okay. What if I drew this one? Let me draw a different one. What if I drew this one? So I'll try to make it the same looking. What if I did this? What if it was NH3, NH3, CN, 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 CN. So look at these two. What are those? Are those also cis and trans isomers? No, what are they? They're optical isomers? They're the same molecule. Yes, they're the same molecule. So you might recognize, again, play the game. How do they differ? Those ammonias are still across from one another. So you might think, oh, but you just like flipped it, you took the mirror image, those are optical isomers. They're only optical isomers when you flip it, you take the mirror image and you get a brand new unique molecule. All right, here I took the same molecule and I just rotated it. All right, so recognize you're still looking at the same molecule. You can kind of think of it as, oh, I'm looking at two trans compounds, two trans molecules. So it's the same, All right, okay, so let's keep going. This one, how do they differ? Right there, linkage, yes, because here SCN, thiocyanide 1, the lone pair is coming from SC, the sulfur, and then the other one's coming from nitrogen. Again, so you'll see those isomers have the exact same formulas, just how they're bonded is different. Cool. These two. So this mirror thing that I drew, I'm trying to show you that these two molecules are mirror images of one another. See, the bromines are the back, chlorides in the front, F's in the side, hydrogen's up top. So these are mirror images of one another. But now the question is, are the mirror images different? Are they different molecules? Yes, they are. So these are optical isomers. Optical isomers. Yeah, so they are in fact different. I promise you, you could rotate this in your mind or in real life if you had a modeling kit. You cannot make these two molecules match one another at all. How you could try to do it is rotate the hydrogen and bromine so they're kind of facing the same way as this molecule, and what you see are the fluoride and chloride are flipped. They're completely flipped from one another, so they're not the same molecule. Yes. So this is something who's taking organic next year, pretty much everyone, yes. So carbon, when it has 4 bonds, okay, coordination number 4, it's a tetrahedron. So carbon is unique in that if a carbon atom has 4 unique bonds, we call it chiral. It's a chiral carbon, meaning that its optical isomer is unique, that it possesses an enantiomer, that how those bonds are oriented in 3 dimensions is important. So that's an idea that you should keep handy for organic chemistry, is that when carbon has 4 different things attached to it, it is always chiral. But if there's only 3 unique things, so for example, if there were 2 hydrogens, I think, is that the next one? Yes. There's 2 hydrogens attached to it, then it's not chiral. So I'll just tell you that. This one is not chiral. So these 2 molecules are what? They're the same molecule. Yeah, you could rotate this. All right, rotate this molecule and superimpose those 2 images, meaning that they're the same molecule. But in this example where carbon has 4 unique bonds to it, it is chiral, or it has an optical isomer. That's another way to say it. All the terms like chiral, enantiomer, optical isomer, all of those mean the same thing, that when you take the mirror image, it's a brand new unique molecule. But in this example, does carbon have 4 unique bonds? No. So this carbon is not chiral. That it doesn't matter how you arrange these 4 bonds, it's not brand new and unique. You actually just get the same molecule. All you have to do is rotate it in 3 dimensions to superimpose them. All right, so we see one of the requirements for optical isomers, all right? Optical isomers mean that you take the mirror image. So the question is, what kinds of molecules, when you take the mirror image, do you get an optical isomer? The first one is when you have a tetrahedral coordination number. And again, you have 4 unique bonds, 4 unique ligands bonds. They have to be unique. 4 of them are unique tetrahedron. That will always yield an optical isomer, always. Keep that in your back pocket for organic. So if you learn anything from this, it'll be useful for organic. Now, the other type of optical isomer comes from octahedral compounds. And so this one is an example of that. All right, so this next one, look at the cobalt. What's its coordination number? 6. So I feel like it's a lot more obvious here that we do see, in fact, cobalt has 1, 2, 3, 4, 5, 6 bonds to it. But how many ligands are there? Only 3, because this is actually our cobalt ethylene diamine 3+ compound, all right? So here you can clearly see ethylene diamine biting twice. Each of like the ammonias that are tethered together, they're biting each, but they just so happen to be bonded to one another, all right? Okay, so this is cobalt ethylene diamine. So, and I tried to make it clear to you, well, I guess not, that these are actually mirror images of one another. They're mirror images of one another. So in this compound, I like to think of those ethylene diamines as like a fan. It's like a fan with paddles on it. It has 3 paddles on it. And if you think about a fan, you know, a fan will only work properly. It'll only blow air when the fan is spinning in a certain direction. If you take a fan and make the blade spin in the opposite direction, will it move the air? No. It'll move the air backwards, essentially. So in this case, when we have like this fan type arrangement of paddles present, we will also get optical isomers, because when you think of about a fan, the blades, they're oriented in a certain direction to make sure that the air movement is in the direction that you want. But if we reverse the directions of the fan blades, we get this unique molecule. And that's what we see here. That in this example, the fan blades, they're moving in this direction. It doesn't matter that if you can see it or not, okay? So this would be an example of the delta isomer. You don't need to actually be able to identify it. I just wanna let you know that there are designations for these types of optical isomers that have this fan arrangement. And then this one, the fan blades move in this direction, the counterclockwise direction. This is our lambda isomer. So these are in fact different molecules. They're fan blades with just different oriented blades. Yes. Okay, so these again are optical isomers. All right. So we see cobalt has a coordination number of 6. It's in an octahedron field. So we will get optical isomers when we have an octahedron with what I call 3 paddles. I like to just say paddles because I don't want to make it too specific and say ethylene diamines, because you could have any bidentate present and you would get an optical isomer. It could be oxalates, it could be BIPI molecules or BIPI ligands instead. You just need 3 paddles to make that fan arrangement to have an optical isomer in an octahedron space. All right. Okay, what about this next one? What is that? So I'm trying to show you that these are mirror images. So are those mirror images optical isomers, or are they the same molecule? What do we think? The same molecule? You sure about that? No. Yeah, they're actually not the same molecule. These are also optical isomers. Yeah, so that is the kind of the last criteria or option for octahedrals. You can also have 2 paddles. 2 paddles. Because here, let me show you this way. So these chlorines, these chlorines, they're identical, right? What if I just did this? Don't that look like a paddle? Oh, doesn't it look like a paddle? So then it kind of, because those 2 chlorides are there next to one another, cis to one another, it kind of completes this cis paddle arrangement with 3 different paddles around our octahedron field. So these 2 molecules are in fact optical isomers as well. To prove it to you, so I like to think of the fan blade. So here that one's moving that way, kind of going front to back. And then this one's moving front to back, is going that way. Is it? Or no, if we're going, Front to back? Yeah, this one. Yeah. It doesn't matter. As long as you know that an octahedron field with 3 or 2 paddles will always make a optical isomer. But those 2 paddles, they need to be cis to one another. And I'll show you an example right here. These 2. Because look, we have 2 paddles, right? 2 paddles. You agree with me? There's 2 paddles there. But what's different with this molecule? These paddles are actually trans from one another. Yeah, they're trans from one another. So actually, let me do this one. Okay, so this octahedron chromium has 2 paddle ethylene diamines. They're trans to one another. What would happen when I take the mirror image? Would you agree that these 2 molecules are mirror images of one another? Yes. Are they optical isomers? No. They're what? They're the same molecule, yeah. So in this example, there's 2 paddles, but they're trans to one another, so they do not make an optical isomer. When you take the mirror image, you get the exact same molecule back. It's only when they're cis to one another, like in this example, where you could have an optical isomer. Where, again, fan blades where the orientation matters. So what would we call these 2 molecules? Are these mirror images of one another? No, they're not. But what are they? They're yes, they're geometric isomers, so are cis and trans version. So you can focus on the cyanides. So here the cyanides are trans, these ones are cis. So these are cis, that is trans. Okay. So kind of putting it all together, which one of these molecules will possess an optical isomer? Does the trans version have an optical isomer? No. But does the cis version? Yes, it does. Fantastic. So this is what I've drawn here is just one example of the optical isomers. All right. So here's my trick. This will get you out of trouble. Those are the criteria to find to identify whether a molecule has an optical isomer or not. Here's my trick. If you have a molecule and there is a mirror plane in a molecule, if there is a mirror plate, if you can place a mirror anywhere in your molecule and you can reflect the same bonds on one side to the other side, okay, it is never going to have an optical isomer. So a mirror plane in molecule will never be chiral, ever, ever. Because if you take a mirror image of a mirror, what do you get? You get the same thing back. So if there is a mirror image anywhere in your molecule, it can never be chiral. So let's go back to this example, this one, where you told me the trans version doesn't have an optical isomer, but the cis version does. So can you locate where the mirror image is, or sorry, the mirror plane in the molecule of the trans version is? Can you see it? There's actually a bunch of places you could place a mirror and mirror the bonds on the top and the bottom or left and right to get that same molecule. So like that blue box, if you just placed a mirror right there and mirrored the 2 cyanides, you see there's a mirror plane. Or you could put a mirror plane like right there and mirror the 2 ethylene diamines. So this is a reason why the trans version does not have an optical isomer. Personally, that's what I look for when trying to determine whether something has an optical isomer or not. I look for, are there any mirror planes present? If there's not, then typically, almost always, that molecule will have an optical isomer. But if there is a mirror plane, then it will not. If you take the mirror image, you'll get the exact same molecule back. And that's something to keep in your back pocket for organic chemistry as well. Okay. Let me go back to this molecule. Does this molecule have an optical isomer? No, because that carbon does not have 4 unique bonds. Can you figure out where you would put where would you put the mirror plane? Where is the mirror plane in that molecule? No, there is. There has to be. There has to be a mirror plane present if this does not have an optical isomer. It's right here. It's between these 2 fluorine-chlorine bonds, and you are essentially like mirroring that hydrogen, those 2 hydrogens. Yep, that's where it is. Yep. I promise you, if something does not have an optical isomer, there has to be a mirror plane in the molecule somewhere, okay? Whether you can see it or not, whether you can see it or not. All right, let's keep going. All right, we said those are the same. What about these two molecules? Are those mirror images? No, but what are they? They're the same molecule, yeah. How did you get there? You just rotated it, yes. Or if you might recognize, oh, this looks like trans cyanides, and this is also trans cyanides. Wow, yeah, and so then in your mind you can think, oh, I can just rotate it. Okay, these two, how are they different? Let's focus on the chlorides. They're all right there. These are there. What are these kind of isomers? They're geometric again. It's not cis and trans though, because now there's 3 ligands that we're tracking. 3 of the same ligands that we're tracking. So when it's 3, we use the designation face and mer. All right, but it's the same idea as cis and trans, that we're looking at those identical ligands and how they're oriented spatially. In face, they all the 3 of the same ligands occupy the same face of the octahedron. Like I could rotate those 3 chlorides and they could all fall on on a table. And then mer is when they're, I guess, like north, east, south. So I think it looks like a mermaid tail. And so there's your other geometric isomer. Okay. Okay, great. Do any of these have optical isomers? Yes or no? Does the face have an optical isomer? If you take the mirror image, will you get a brand new molecule? No, yeah, neither of these actually have optical isomers. They have mirror images. Where are they? Where are they? Right here. So if you put a mirror plane right there, kind of bisecting those chlorines and ammonias, that you will reflect both of these across that mirror plane. Okay. I feel like the mer is easier to see. Does the mer version have an optical isomer? No, it doesn't. Again, our mirror plane here could be these 4, the bonds that make up, or the plane that make up these 4 bonds. And so you're reflecting those 2 ammonias on each side. Yeah, so neither of these have optical isomers. I promise, once you see enough, it'll just all click. I saw in office hours. Students came in, they didn't understand this at all, but I did enough of them, and then it just hit them like a brick wall, and then they started seeing it. Okay. This one, these 2, what are these? These are the same molecule, yes. So you can focus on the chlorides or ammonias, it doesn't matter. And so in my idea, these are both trans molecules. All right, but what I was trying to get you to think was, oh, I took the mirror image, then these must be optical isomers. Just because I take the mirror image doesn't mean that it's an optical isomer. It's only an optical isomer when it's unique. And so these 2 molecules are actually the same molecule. You know, I could also draw the cis version of this platinum guy, but I didn't. But these are the same molecule. Because platinum, what's the geometry around that platinum? It's not tetrahedral, actually. It's square planar. Yeah, so it's square planar. And so something interesting about square planar molecules is, since the molecule exists on a plane, the molecule itself is its mirror plane. All right, so a square planar molecule will always have a mirror plane. So square planar molecules never have optical isomers, because the idea is this molecule's flat. So if you put a mirror flat on the table as well, platinum doesn't have any bonds above it or below it. So if you mirror image nothing, you get nothing on each side. So the molecule itself is a mirror plane. Okay, all right, good. Are we good with that? So let me just go back up here about our optical isomer requirements. Tetrahedral, 4 unique bonds. Octahedral, so that's a coordination number of 6. Either having 3 paddles will always, its mirror image will always be unique, or 2 paddles if they're in the cis arrangement. If there's a mirror plane in your molecule, it can never be chiral. ever. Okay, so let me just for funsies draw one. Okay. What's this shape? What's that shape? Octahedral. Okay, so what if I had this molecule? Is that molecule chiral? No, why? There's a mirror plane in it, yeah. Or draw it, draw the mirror image and just see if you can't rotate it in your mind and make them match. Okay, yeah. Okay, what about this? Does this have an optical isomer? It's not this. If you mirror image it and it's not the same molecule, what does that mean? That's an optical isomer, yes. So this molecule does in fact have an optical isomer. Here, just squint your eyes and just connect A, and B, B. What does that look like? 3 paddles, yeah. Or the last one I did, right? I did like A, B, B or whatever. Right? I did this one and you right away are like, no, that's not an optic, that does not have an optical isomer. And the reasoning, you could kind of for the same reason, connect those 2 B's and you see, oh, like if you reflect the A or the mirror plane is those 2 paddles, you get the same thing on the top and the bottom. This picture is really no different than this one. Yeah. Okay. Good? Yeah. I mean, the worst that can happen, right, when you're asking about optical isomers, it's going to say, does it have an optical isomer or not? And you have a 50-50 chance, right? So it's honestly, it's either you see it or you don't. But learning how to see it, it just comes with time and practice once you look at enough of them. Yeah. So the question is, when I said the 2 paddles and they're cis to one another, what is that referring to? So for this example, that both of these molecules have 2 paddles, right? But in one of them, you can think of it both ways. You can think of it as the paddles being cis to one another, or the other ligands, they're also cis to one another. This does have an optical isomer, while the trans version, so the other ligands are trans to one another, and the paddles are trans to one another. This does not have an optical isomer. Does that make sense? And I think if we go back to this example also, I would say, yeah, if you're looking at the other ligand, A and A are trans to one another, but in the example where we did have an optical isomer, where it was A, B, B, A and B are cis to one another. That makes sense? Yeah, all right. Okay. Nuclear chemistry. All right. So who here, and I just want to see it in a show of hands, other lecturers, people who have different lecturers, who was the last chapter was nuclear chemistry? Or did you do it before transition metal? You did nuclear after transition metal? Did anyone do it before? No? You did it before? Okay, all right. I like to save nuclear for the end, because up until now, we've talked about electrons for the last 9 months. But in nuclear chemistry, we finally can ignore electrons, and we don't have to balance them anymore. Because in nuclear chemistry, we're looking at really high energy reactions, alpha particles, beta particles. These are all coming from the nucleus. And because they're so high energy, we don't care about balancing charges, because these reactions, they're just going to grab electrons from wherever they can. All right, so the idea here with nuclear decay equations is understanding the identity of these sources of nuclear radiation and understanding their mass requirements, essentially. So our first one is an alpha particle. It's a helium nucleus, so the mass number is 4, and there's 2 protons present. So if it's a helium nucleus, there's no electrons present, so technically alpha particle has a +2 charge, technically. But again, in nuclear balancing, we don't care about charge, so we just ignore it. And so as long as you keep track of the number of protons and neutrons in your balanced equations, then these solve themselves essentially, all right? We just need to make sure things are mass balanced on each side. And so the idea here, so that's an alpha particle. A beta particle is 0 and -1. What else is there? Gamma, what is gamma? 0, 0, it's literally pure energy. Then what else did we talk about? Positron emission is 0 + 1. And then the last one is, what is it? Electron capture. So it's 0, -1, but it's a reactant. So the idea here is let's do a little bit of reading comprehension. Copper 66 is emitting a beta particle. So that implies the beta particle is what? A reactant or a product? A product, yeah. So we're going to put copper 66, but I don't tell you the number of protons. But thankfully you have your own cheat sheet that tells you copper is 29 protons. So from that you can deduce the number of electrons. So copper is emitting a beta particle. So I know that beta 0, -1 has to be a product. So we just balance it to make sure all those numbers match up. So the mass number of our product has to be 66. And then how many protons does our product have? 30, yep. And then what is that? Zinc, yep, that's it. Okay, and so you can do that for all of these. Alpha particle emission, your product is an alpha particle. Find the missing piece. Positron emission, so you understand that this is your positron, 0 + 1 electron. This is your product. Find the missing piece, all right? Electron capture of calcium 39. That's the only one that's different. Electron capture, the electron isn't your product. The electron is now your reactant. So identify what calcium is. It's calcium 38. So calcium has 20 protons, 38. Mass number plus, we're capturing an electron and it makes something, it makes one product. And so we just balance those numbers. So we have a mass number of 38, but our number of protons is 19. This is potassium. Yay. So that's it. Really just understanding what these particles are. Are they a product or a reactant? And so using reading comprehension, emission implies that the particle is a product. Capture implies that it is a reactant. And so once you have that particle on the right side, the number should just fall out and you should be able to identify it. And again, we don't have to worry about actually balancing charges, thank goodness. All right, let's balance these transmutations. It works the exact same way. Balance mass numbers and protons, find the missing piece. So for this one, I like to just sum up both sides. We have a total of 31 mass number, 15 protons, and then you just make sure the sum of the product side matches that. So we have also a neutron being emitted as well. So our product is going to have a mass number of 30, 15 protons, what's that? Phosphorus, cool. All right, so transmutations is atom smashing. We smash a alpha particle at a aluminum atom and we can transform it into phosphorus. I mentioned to my class at least, one of my pet peeves for, in 1210, 1220, we used to make students write full-blown lab reports. Yeah, full-blown lab reports, discussion section, all that. So in the day and age of chat GPT or whatever, like that'd be awful, right? Of those lab reports. But now, with smart worksheets, it makes grading and everything easier. I think students get more out of it. I know most of you hate smart worksheets, but I just want to tell you that the alternative is a lot worse. Yes, yes. It's a lot worse. And so when I was a graduate student here, I would read these awful, awful lab reports. They're just awful. It's all right. I would always be really hard on the first ones, and then they would get better and better in time. And so once by the end of the year, you know, students started writing good lab reports, I would nitpick a lot. And some of the things I would nitpick is when students would say they created something. They would like pour two chemicals together, that a reaction would happen, and they'd be like, I created lead iodide. And I'm like, no, you did not create it. You synthesized it. So you gotta be specific with your language, because creating something, I don't know, there's like a magical aura about it, like you just like made it out of nothing. No, you just mix two chemicals together and the KSP of lead iodide is really low. You know, you synthesized it, you didn't create it. But with nuclear reactions, you do in fact create things. So I only use the word create when it comes to nuclear chemistry, but not with all the rest. So just be, you know, careful with your language when you're writing like technical reports and stuff. Create has a very, I don't know, magical feeling to it. Try words like I designed, I synthesized, I formulated. I don't know, those sound smarter, like I just, create just sounds like you took it out of nothing. I don't know. Okay. All right, so that's my soapbox. All right, what's the product here? Or sorry, no, the reactant. So here, 243, 96, so this has to be 2 and 4. What is that? That's an alpha particle, great. Or helium, nucleus, whatever. Okay, great. All right. Now putting it all together. All right, yes, we were able to predict, you know, beta alpha emissions, but the idea is, well, how can we predict what kind of radioactive decay elements typically take? So what we see here, especially up here, like when we did the copper example, a beta emission results in a zinc atom. If we actually did the alpha particle emission, what was the answer? It's something else. It's not zinc. It's something else. Cobalt. All right. So if we did an alpha emission of copper 66, we would get a cobalt nucleus. So cobalt 62, 27, something like that. So the idea here is, depending on the type of emission that's happening, we get different products. So why do certain elements do alpha versus beta emission? And how we predict it is based upon the band of stability. All right, so depending on the ratio of neutrons to protons in a nucleus, there's a certain ratio that is most stable. So when we're above or below that, what we call band of stability, so that kind of perfect ratio between neutrons and protons, we can predict whether something undergoes beta emission or positron emission. So here are the rules, all right, for predicting what type of decay process happens. The easiest one is anything that's above 83 protons. Anything that's heavier than bismuth will always undergo what kind of emission? Alpha, always. Those are the easy ones. So anything heavier than bismuth will always undergo alpha decay first. And the reasoning is, so the blue dots you see here are stable nuclei, yellow dots are just any nuclei. So if we're way beyond bismuth, if we're over here, when we emit an alpha particle, we lose 2 protons, 2 neutrons. So what we do is we move towards, diagonally, the belt of stability, all right? That's the first one. Okay, the second criteria is if we are above the belt of stability, so your calculated neutron to proton ratio is above what's typical. What kind of emission happens? I forget. Is it beta? Yeah? Is it? What does my key say? I always forget. Yes, it is beta emission if you are above the belt. Okay? And in doing so, if we're above the belt, we're like here, what beta emission will do is your product will be closer, it'll go down, closer to the belt of stability. It'll lower your neutron to proton ratio. right? Until it becomes stable, your nuclei becomes stable. And the last one is if you're below your neutron to proton ratio, then you typically will do positron emission. So 0 plus 1. And again, because doing so, if you calculate the product, your product has a higher neutron to proton ratio. So all of these questions dictate, can you calculate the neutron to proton ratio and predict which way, what kind of emission do you need to become more stable? And so in this example, you know, I have the graph here, so you can see, okay, where is it stable? Am I above or below? But technically in all of these examples, it's quite obvious if you're above or below the belt of stability. Because typically, at least for light atoms, the lowest neutron to proton ratio is 1, where there's an equal number of neutrons and protons. So if you have a neutron to proton ratio below 1, you are obviously under the belt of stability, because under 1 is never seen for stable nuclei. Right? So let's just go through these. Potassium 40, what kind of decay would you expect? This would have us just calculate what is the neutron to proton ratio. Potassium 40, does that mean that there's 40 neutrons? No, this is your mass number. So this is neutrons and protons. So potassium has 19 protons. So therefore, how many neutrons are there? 21. And so what is that number? Thank you, 1.10. So are we above, below, or at the belt of stability? Above, so this is going to undergo beta emission. Both. Yeah. Because it's potassium's quite a light element, so its neutron to proton ratio should be 1, but we're above 1, so it's going to undergo beta emission. So what would the product be? So K, 19, 20, it's a product. What's our other product? Oh, it's 40, sorry. 40, 20, calcium. What's the proton to neutron ratio there? Or sorry, neutron to proton ratio. 1, is that stable? Yes, it is. Yeah, so if you for some reason forget this, okay, just try all of them. Try all of them, calculate the new neutron to proton ratio and see how can I get more stable if you forget these. Okay, plutonium. Do I actually need to calculate the neutron to proton ratio? No, because what's going to happen? Alpha, yes. I don't feel like writing what the product is. Oxygen 14. Neutron to proton ratio. Oxygen has 8 protons. How many neutrons here? 6. So this is obviously less than 1. So what decay is going to happen? Positron emission. Yeah, so E0 plus 1. So for funsies, let's get the product. So a positron is being emitted. What's the product when oxygen 14 undergoes positron emission? So what's our product? 14, 7, what is this? Nitrogen. What's the nitrogen to neutron to proton ratio there? 1. Do you think nitrogen 14 is stable? Heck yes, it is. Yes. And so again, if you forget if it's beta or positron emission, try both and see what the product is, see which one gets you in the more stable direction. So the question here on the chat is the band of stability given on the test? If it is not obvious, if it's above or below the belt of stability, then we have to give you it. But in all of these examples that I've showed, our neutron to proton ratio was obviously above or below. You technically don't need it, right? Okay. I actually didn't answer a lot of these questions. Can you explain the molecule that is the same? Okay. Okay. Are trans isomers usually the same molecule? Yes, they are, because in trans molecules, there's always a mirror image present. Do I have an example of a coordination sphere isomer? Oh yeah, you're right, I didn't do that. Oh, and here's a question, is potassium 40 stable 2, or no. It's not super stable, so potassium 40 dating is a thing. And here's the way I like to see if something's really stable or not, is I look at the periodic table and I look at the molar mass of potassium. What is it? 39.1 is potassium. So what mass number potassium is most stable? Potassium 39 is the pretty much the most stable potassium. So potassium 40, not super stable. Yeah, okay. So someone wanted an example of a coordination sphere isomer. Yeah, that's one I didn't give. So let me do one real quick. This would be an example of a coordination sphere isomer. So if I did boop, boop, chloride, chloride, all right? And let's say all of this was positively charged and there was a bromide on the outside, all right? So there's my complex. It's an octahedron, 2 ethylene diamines, 2 chlorides. This would have a, this is chiral, that it would have an optical isomer. I've just drawn one for fun, right? So here's one molecule. This molecule's coordination sphere isomer would just be if the chloride and the bromide swapped places. So if I redrew this, if I redrew it, I would redraw it with a bromide drawn there, and then the chloride would be on the outside, on the outer thing. Mastering stated that the neutron to proton ratio, anything with 40 AMU should be about 1.25. I don't think that's true. 1.25. So here are some examples of stable neutron to proton ratios. So for oxygen, it's close to 1. For iron, it gets close to 1.15. So iron has a mass number of like 55 or 50, 56 mass number. And then once you get to iodine, 127, it gets closer to 1.4. So 1.25, what you're referring to, is over here. So things that are heavier than iron, I would check those numbers again. I'd check those numbers. Okay. All right, so let's keep going. All right, so let's talk about decay chains. So just because something's unstable, just because it's radioactive, doesn't mean that when it decays, it automatically becomes stable. For some substances, multiple decay modes will happen before it becomes a stable nuclei, typically something that's lighter than bismuth. So for example, the thorium decay chain has a bunch of different emissions that happen until it becomes stable again. So here, these questions, it's not about, do you know the steps of the decay chain? It's, can you predict the product after we give you what steps in the decay chain happen? So thorium 232, what's the thing? Protons 90. So I'm telling you that alpha, 2 betas, and 2 alphas occur. What's the product? So again, as long as you know that an alpha particle is 2 protons, 2 neutrons, you should be able to predict what the product is. And then after you form that product, then beta emission occurs. So you just have to kind of sum up all of these separate steps to see what you actually get at the end. So if we do an alpha decay of thorium, we make 88 and 228. Okay, whatever product element that is. I technically don't, since this isn't my answer, I don't really need to get what element it is. I can just move on to what if beta emission happens then. All right, remember, emission implies that the beta particle is the product. So the new product along with the beta particle is 228, and what? 89? Yeah, okay. All right, and then another beta emission happens. Again, I don't really need to identify what it is because I'm just balancing the numbers. So beta emission will give me 228 and 90. Oh crap, now I have thorium again. So that's interesting. These decay chains, sometimes we go up in mass, up in identity, down, it's not just a straight path down to stability. And then what's next? 2 alphas. So an alpha would be 224 and 288 again. And then another alpha decay, and again, all of these emissions, they're all products. Then it would be 220 and 86. What is that? What is it? 86. Radon, yay. Oop. Okay. So in this example with the decay chain, it's just a bunch of decay processes, all right after one another. All right, and then the last learning objective for nuclear chemistry is kinetics. So this is actually chapter 14 review. Remember when we talked about kinetics in chapter 14, reaction order was important. We had to look at experimental data to see was something zeroth, first or second order. But the nice thing about nuclear decay, it always follows what kind of order? First. So all the equations for first order reactions, you're given those, right? So the first order integrated rate law is natural log of concentration at some time equals natural log of your initial minus KT, right? But K refers to rate constant, and so we talked a lot about rate constants in chapter 14, but in terms of nuclear chemistry and understanding, how our samples disintegrate, oftentimes it's easier for us to report what the half-life is of a substance. And so we have another equation to relate to half-life, and that is your half-life for your substance is related to the rate constant, where it's natural log of 2 over your rate constant is your half-life. And really, these two equations are the exact same, where natural log of 2 comes from when you do natural log of 50% equals natural log of 100% minus KT. This is your T1/2. These two equations are actually the exact same, mathematically. And you can prove it to yourself. I think there's like some interesting rules with natural logs. If you subtract them, then they become division. I don't know what those rules are, but if you check in your calculator, you take natural log of 2 and you do natural log of 100 minus natural log of 50, it's the same number. It's the same number, yeah. So these are the exact same equation. Okay, so those are the equations that we're gonna use. So let's relate it to this actual question. Really, this question is no different than chapter 14. It just has to do with radioactivity, which we understand is first order. So I give you the half-life of cobalt-60 used in nuclear medicine. What fraction of cobalt-60 remains after 8 years? So, we need to use our integrated rate law for this. They're telling us that T is equal to 8 years. The half-life is 5.3 years. So if we look at our integrated rate law, we don't have half-life in here. It's rate constant. So we just need to convert that half-life into a rate constant that we can use for our integrated rate law. So don't try to put 5.3 years inside here. It's not going to work. Also, don't try to put 5.3 years in our half-life equation. This equation just tells us, makes the relationship between our rate constant and the half-life, because it's easier to think about half-lives instead of rate constant. So the idea here is I want to use that 5.3 years to calculate our rate constant. So 5.3 years is my T1/2 equals natural log of 2 over K. And so that should allow me to calculate what K is. I think this equation in the supplemental handout, natural log of 2 is equal to 0.693. I just like to write natural log of 2 because that 2 is significant. It's, again, solving the integrated rate law. All right, and so then if you calculate for what K is, because that's the value we actually put in our thing, in our integrated rate law, we get K is equal to 0.1308 years to the -1. right? And then that's the value that we put into the integrated rate law. All right, so this question is asking what fraction of sample remains. So it sounds like we're solving for concentration at some time, but what I don't give you is the initial concentration. So you have to make an assumption. How much sample do we start with if we're talking about fractions? 100%, yeah, 100% or 1, it doesn't matter, however you want to think about that. So concentration initial, I'm just going to say is 100% or 100, whatever. So I'm solving for that concentration at some time. So natural log of concentration at some time equals natural log of 100 minus 0.13068 years to the negative 1. That's K times the actual time that has elapsed, and that's 8 years. All right, and when you solve for that, and then you take the e to both sides to undo the natural log, you get that 35.1% remains. That's how much is left. All right, so a couple things here to make sure that, like, intuitively this answer makes sense. If we started with 100% and we ended up with 35%, has more or less than a half-life elapsed? More. What time were we actually given? 8 years. Is that more or less than a half-life? More. So does this answer make sense? Yes, it does. Very good. Very good. Okay, good. Another question that someone else asked me is, does the units for the integrated rate law here matter? And they don't. They don't matter as long as they're the same. So see, in this example, I have these in percentages, and that's fine. And the reason why concentration doesn't change, make a difference here for our integrated rate law for first order reactions is look at the unit of K. See how the K unit is just time? There's no like concentration unit in there at all. So it doesn't matter what the value of A sub T and A sub 0 are, as long as they're the same. They could both be gram amounts, they could both be percentages, they just have to be the same. And it's because of the unit of the first order K rate constant. Yeah. You could calculate, so the question is, would you need to calculate the half-life for a 0th or second order rate constant reaction? You could, but it would be a chapter 14 question, not a radioactivity question. Yeah, and you could. And they're given. Those are given. Yeah, okay. Okay, let's do one more. All right, so a certain radioactive substance reduces by 35% after 2 days. Let's get the rate constant, the half-life, and the percentage of the sample left after 7 days. Okay. So first order, we just need to make sure we plug in the right numbers. So 2 days, that's T. Reduces by 35%. That implies I'm trying to tell you a little bit about concentration after some time. Is the concentration, if we start at 100%, how much do we have left after 2 days? Is it 35% we have left? No, yeah, no, it's 65%. Reading comprehension, yes. All right, so hopefully you see this is all the information you need for an integrated, the first order integrated rate law. So natural log of 65 equals natural log of 100 minus K times T, which is 2 days. And again, I told you that the unit of concentrations doesn't matter for first order. If, I just put these as percent whole numbers. If you did it at 0.65 and 1.0, you will get the same answer, I promise. You'll get the same answer. All right, and then we solve for K. K is equal to 0.215 days to the negative 1 because of the unit of time. Okay, so that's our rate constant. We could then go ahead, let's just do C a while, where it's calculate the percent of sample remaining after 7 days, because we have K now, and we have a new time, where time is equal to 7 days. So we just have to use the integrated rate law again but just with this new time variable and the rate constant that we just calculated. So we are solving for concentration left. So natural log of A sub t equals natural log of 100 minus that K we just got, 0.215 days times 7 days. All right, so 7 days have elapsed instead, and we get the concentration after some time is something like 22.2%. All right, so that was C. So I just kind of blew ahead since we already got K. We can just plug in the appropriate time. And now going back to B, we want to calculate the half-life, because I don't know about you, but that K, rate constant, like, it doesn't really mean anything to me. It's a number, but I can't get a grasp of like how fast the reaction decays. So that's why we oftentimes talk about radioactive decay in terms of half-lives, where, okay, you lose half of your sample in this amount of time. I understand time. I don't understand inverse time, all right? Unless I have an integrated rate law and I can calculate it. So it's oftentimes easier to just read and understand and appreciate half-life values. So T1/2, natural log of 0.215 days. And I think if you calculate that, you get something like 3.22 days is the half-life. So that makes more sense. Okay, you lose half your sample in 3 and some change days. That makes more sense to me. Okay, all right. I always, again, like to think about reasonable answers. Let's look back at C, where I said, okay, in 7 days, this reaction will have 22% of the sample left. Does that make sense in terms of the half-life? The half-life is 3-ish days. The time that elapsed is 7 days, so that's about 2 half-lives. So we have less than a quarter left. So yes, that answer makes sense. Okay, when you have answers like, you know, you have 89% left and 3 half-lives have gone by, that's when things don't make sense, and hopefully you can retrack your work to re-arrive at the right answer. Okay, all right, that's it. That's chapter new stuff. Okay, what chapter midterm stuff do you want to review? Okay, we're gonna do one. We're just gonna go in order. All right, benzene, midterm 1. So midterm 1 was about solutions, colligative properties, freezing point depression, boiling point elevation, vapor pressure, and then kinetics, everyone's favorite kinetics. So benzene was once commonly used as an organic solvent. What substances are miscible with benzene? Miscible means what? Mixes. Things that mix have what kind of intermolecular forces? Similar and or strong. Similar and strong. Actually, I guess a blanket statement would just be strong. Strong intermolecular forces, most commonly seen with similar IMFs. All right. Okay, so benzene. What kind of IMFs are present in benzene? LDF only. Yes, because it's carbon and hydrogen. So will benzene make strong IMFs with water? No, because water, its highest IMF is hydrogen bonding. So there's IMF mismatch. Bromine. Yes. What about sodium nitrate? No. What IMFs are present in sodium nitrate solid? Ionic. Yeah, so ionic. So there's a mismatch there. Bromine, its highest is LDF, and water is hydrogen bonded. Great. Yes. Let me change this to, okay, so you guys said, right, that things mix when IMFs are similar. That's like how biologists talk about mixing, where they say like dissolves like, but that's kind of wrong a little bit, because the idea here, let's think about it. Will sodium nitrate dissolve in water? Yeah, salt and water. Salts dissolve in water. Do they have similar IMFs? No. Yeah, does sodium nitrate have hydrogen bonding? Then why does it mix? almost polarity, but we actually create a new IMF when we mix salt and water. What IMF is that? Ion dipole. Ion dipole is one of the strongest IMFs out there. So there's an example where water and sodium nitrate mix, not because IMFs are the same, they match, it's because that we create this new stronger IMF, ion dipole, where the polar water molecules solvate your salt, your cations and anions. So the idea, you know, in bio, we learn like dissolves like. I don't know about you, but NaCl, sodium chloride, doesn't look anything like water, yet it still dissolves. And it's not because IMFs match, it's because the IMFs that you create in that solution are really strong, specifically because of ion dipole. Okay. All right, that's my soapbox. All right, let's do this. Density of something is that. What's the molality of the solution? So let's go over our units of concentration. Molarity is what unit? It means moles of your solute over liters of solution. And when I say solution, what does that include? Your solute and your solvent. Okay, all right. What is the unit of molality? Little m. Moles of solute over kilograms of solvent. Great, yes. For funsies, let's just do mass percent. Mass percent is mass of your solute over mass of your solution. And again, solution means solute and solvent. Okay, what about mole fraction? We'll say solute. Mole fraction is your moles of your solute over the total moles of your solution. So moles of your solute plus moles of your solvent. Okay. Okay. All right. So I think I said this last time, but I'll say it again. All of these live on an island together. As long as you know the identity of your solute and your solvent, you can intermix between all of these, no problem. You do not need density. You can just right? You could, if I know moles of solute, do I know the mass of solute that's there? If I know the identity, the molar mass, yeah. If moles of solute, oh, you use moles of solute in mole fraction as well, great. If I know the kilogram amount of solvent, do I know the mole amount of solvent? Yes, all of these are interchangeable as long as you know the identity of your solute and solvent and their molar masses. Where things are different is molarity. Molarity lives on its own island, where if you want to go from molarity to any of these, you need density, yes, and density is grams per milliliter, right? Because if I right now know the liter amount of solution, right, that's the volume amount, but if I know the density, I can get the gram amount of solution, right? Gram amount of solution, and isn't the gram amount of solution in the mass percent? Right? And as long as you know the identity of your solvent and your solute, you can kind of pull out how much kilograms of solvent versus kilograms or mass amount of your solute you have, right? So that's how I like to think of it. All of these live together. You don't need density for molality, mass percent, mole fraction, but you do need density if you want to hop on this island where molarity lives. Okay, so I'm giving you the hard one. I'm giving you molarity, and we want to go to molality. So the strategy here is recognize what molarity is. If I say it's 0.872 molarity, what this means is I have 0.872 moles of that solute, which is potassium chromate, in 1 liter of solution. Just understanding the unit. So my goal is to get it into molality. So I need to figure out how many moles of solute I have, and I need to figure out how many kilograms of solvent I have. So do I already know one of these? Yeah, I know the numerator. I'm halfway done. I'm halfway done. So in my numerator, I'm putting 0.872. But I need to figure, now the hard part is I need to figure out how many kilograms of solvent I have. Right now I have liters of solution. So this is where I'm going to use the density equation. All right, so 1 liter is 1,000 milliliters. The density is, what is it? Where's the density? Oh, it's right there. So it's 1.129 grams equals 1 milliliter. So 1 milliliter on the bottom. This sample weighs, all right, grams. It equals 1,129 grams of solution. But the problem is that gram amount of solution includes what? Can I just put this in the denominator? You might think, oh, you got to convert it to kilograms. No, I can't just convert it to kilograms. So this sample isn't it's 1.129 kilograms of solution. Is that kilograms of solvent? No, because solution means solute plus solvent. So I need to figure out how much solute is present, because if I figure out how much solute is present, I can figure out how much of that mass is solvent. How can I get the mass of solute present? You already have mole amounts, yay! So if I know the mole amount, can I figure out how much that weighs? Yes, so that mole amount, 1 mole is 194.19 grams. All right, and that equals something. 169.3 grams of solute. So that means with this number and the mass of the solution I just got, that the mass of my solvent is just the subtraction of those two numbers. So 959.7 grams of this sample is actually water. And then that is what I want to put in my denominator. All right. So molality here is equal to that 0.872 mole amount divided by 0.9597 kilograms. And so whatever that number is. Okay. All right. So big things with these conversions, understand, you know, the units of each of these, what's molality, mass percent, whatever, and distinguish between, is that value talking about the solute, the solvent, or the solution? The solution is the solvent and the solute. All right. So masses are always additive. So if you know the mass of solute and solvent, you know the mass of the solution. If you know the mole amounts are also additive. So if you add up mole amounts of solute and solvent, you'll get mole amount of your solution. But liter amounts are not additive. Yes, they're not additive. But masses are. Okay. Let's keep going. Okay, this one's too much math. Just look at the key. I want to do short ones. All right. So I'd rather talk about you know, conceptual things and strategies to use and understand, okay, you know, how I've phrased this question, what's the question actually asking? And these are the questions you want to ask yourself on the final, you know, what is the nature, what kind of learning objective is the final exam question asking? So here in this example, I say, okay, using ion pairing, rank these solutions in order of increasing freezing point. Okay, so freezing point, when we have mixtures, all right, as your concentrations of stuff increase, typically what happens to your freezing point? It goes down. Yes, freezing point depression. Salted roads, they freeze at a lower temperature than pure water, right? That's why we throw salt on the roads, is to lower the freezing point of water so it delays before they freeze over. So really this question is asking, can you order these in order of increasing or differing concentration? So we want increasing freezing point. So if we think about freezing point depression, you know, the most concentrated will have the lowest freezing point, while pure water will have the highest freezing point, highest. So right off the bat, I know that pure water, it's going to have a freezing point of 0. Everything else is going to have a freezing point less than 0. But we need to think of, okay, which ones have the most solute particles present in solution? That will have the lowest freezing point. So if we recall the equation for freezing point depression, delta T freezing equals IM KF. All right, so KF is the constant for freezing point depression. It's the same value for all of these. So what we actually want to inspect is what is the product between I and M, molality. So I give you molality in all of these. What is I, you recall? Van 't Hoff factor. So it's the amount of actual ions that dissolve in solution. So you need to think about electrolyte character. Is it a non-electrolyte or is it a strong electrolyte? That will tell you what I is. So glycerin, what's the Van 't Hoff factor in glycerin? 1. So its I times M is 0.2. I'm just going to calculate the true I times M, and then I will consider ion pairing after that. All right, KCl, what's the Van 't Hoff factor of that? 2. So its I times M is 0.2, right? Because potassium chloride, when you stick that in water, it doesn't stick together. You separate potassium plus cations and chloride minus anions. You put one thing in water, you get 2 things out. So you get twice as much ions dissolved. So the I times M here product is 0.2. Do you see the problem that's happening? Yes, okay, so what is the I times M for calcium sulfate? Also 0.2. What about calcium chloride? 0.3, oh, thank goodness. At least one is different, okay. And then I times M for pure water is 0, so there's no freezing point depression, okay. So of these, which one's gonna have the lowest freezing point? The calcium chloride, yeah, because 0.3 is the highest I times M, so it's going to have the largest freezing point depression. So it's the calcium chloride is first. Okay, but hopefully you see the problem here. We have 3 substances that have all the same I times M. So you would think, oh, they have all the same freezing point depression, but that's not true, because now we want to consider ion pairing, where depending on the size of the ions, the charge, and the concentration, we actually see deviations from the Van 't Hoff factor. That the only kinds of compounds that have pure Van 't Hoff factors that we predict are non-electrolytes. So something with a Van 't Hoff factor of 1, like glycerin, its I times M will actually be 0.2, that there is no deviations. Glycerin has no ion pairing. So no deviations. Also, let's think about it this way. Does glycerin have any ions? No, so it can't ion pair. It can't ion pair. So you're not going to have any deviations from the Van 't Hoff factor. Its I times M is going to be exactly 0.2. Now we want to see, okay, how does KCl and calcium sulfate, how do those deviate? Will they be not 0.2? And that's what in fact happens. So we see here, both of calcium chloride and calcium sulfate, they are composed of ions, so they do exhibit ion pairing. So the criteria for ion pairing, typically we see deviations, meaning a less than predicted Van 't Hoff factor. That's what ion pairing basically means, is we see that effect happen when concentrations are really high. We see it when the ion charges are high, or when the size of your ions is small, meaning charge density, right? So ion pairing will happen more if your ions are really small and highly charged, right? So we have potassium chloride and calcium sulfate, which is, calcium +2, sulfate -2. Which one of these do you think does ion pairing more? The sulfate, yeah. So this one will have a I times M that's much less than 0.2, and calcium chloride will have, or potassium chloride will just be a little bit less than 0.2. So the true ordering here is going to be calcium chloride, calcium sulfate, KCl, oh wait, where did I put glycerin? Oh no, oh no. No, let me think about this again. So more concentrated, lower freezing point. So no, it's going to be glycerin, then it will be KCl, then it will be calcium sulfate. Yeah, sorry about that. Then it'll be water. And again, it's because of you're thinking of more particles in solution, lower the freezing point. Calcium chloride has the most particles because its I times M is the greatest. Then next up, I times M, this tells us number of particles, will be glycerin because it's exactly 0.2. Then it'll be KCl because it's just a little bit less than 0.2. Then it's calcium sulfate because it's a lot less than 0.2. And then it's pure water. All right, and so the strategy would be the exact same if I said boiling point elevation. It'd be the exact same, except maybe the ordering, it would just be flipped or whatever. But same idea, you want to calculate I times M. Okay, yeah. Okay, all right. How do I determine I? It's the electrolyte character. So it's what ion, think about the net ionic equation. If you put KCl in a net ionic equation, how would you split it up for the total ionic equation? Okay, I have 12 minutes. So does someone have a number on here they want covered? Number 16? 17? Okay, yes, mechanism. So the reaction order of NO with O2 is believed to occur with the following mechanism. What would the rate expression be if the mechanism is correct? All right, so rate laws are based upon observations, on data, not on balanced equations. So you might look at this balanced equation and think, oh, it's second order in NO, first order in O2, because that's what the coefficients say. That's not quite true. We need to actually look at, okay, what are the elementary steps that make up this reaction? It may or may not include O2 at all. We'll see. So the idea with mechanisms is each of these given steps is an elementary reaction where you can just take the reactants to get the rate law. But the idea here, when something's multi-step, is it's the slow step always determines the rate law. The slow step always determines the rate law. So if these are elementary steps, that means that the rate law for this reaction is rate equals K, the second step times NO3 concentration times NO concentration. All right, am I done? Can I just walk away? No, what's the problem? NO3 is an intermediate. Yes, it's an intermediate. So I need to get rid of it. How am I going to get rid of it? With the fast step. Yes, so with the fast step, this is an equilibrium. So I'm going to say the forward reaction is equal to the reverse reaction. The rate of the forward is equal to the rate of the reverse. So K of the forward reaction times NO times O2 is equal to the rate of the reverse reaction. So it's basically reactants equal products just multiplied together. So K of the reverse reaction, NO3. And so we can see, oh, this is how we're going to get rid of NO3. We see that if we divide each side by K, all these K's just kind of blur together. We can't typically calculate the K of each individual step. We do, in fact, see that our intermediate concentration is equal to or proportional to the NO concentration times the O2 concentration. And so that allows us to insert that variable into the NO3 we want to get rid of. So now we do see, in fact, that the overall rate law for this reaction is K times NO squared times O2. Okay, so in this example, the balanced chemical equation is the rate law, but for on an exam question, it would never be that way, because we know that half of students will just look at the balanced equation and give that rate law, but what we actually want you to do is the learning objective in which you inspect the individual steps. It just so happens this one does end up equaling our balanced chemical equation. Yeah, so it's the slow step always determines the rate. And I don't know if you remember the exam question. I thought it was a really good exam question where, so in this one, the slow step's the second step. I don't know if you remember the exam question. What was it? It was the slow step was the third step, but I never taught you that. That's not fair. No, you do the exact same things. The idea there was that you just had two intermediates, right? You had two intermediates, so you had to use both of the fast reactions. You had to use step 1 and 2 to get rid of it. That was it. So, yeah. All right. All right, next one. 8, okay, we'll just keep going. All right. Oh, it's the same reaction, okay. But this is based upon data, right? So here I give you initial rates with different initial concentrations, and we ask you to get a rate law. So this is how we get orders, the order of our reactants for our rate law. So the idea here is you just want to look at experiments where only one thing changes and inspect how the rate changes. So if I look at experiments 1 and 2, I see that O2 doesn't change its concentration between those two experiments. So O2 is not contributing to any changes of the rate. But I see that the concentration of NO, what happens? It doubles. How does the rate change? Does it double? No, it quadruples. So if I double the concentration of a reactant, but the rate quadruples, what's the order? Second. So this tells me that NO is second order. So then we do the same thing for O2, where we inspect two reactions where it changed. Oh, well, now that we know the order for NO, we could apply that to any rate changes. But what's easiest here, since it's already given, is look at 2 and 3, where now NO is not contributing to any changes of rate, but I see O2 doubles. And then how does the rate between 2 and 3 change? That doubles. So the order of O2 is 1. Okay. All right. So this is not the full rate law. So rate equals K. So second order NO, first order O2. This isn't quite the full rate law. I can get K, my rate constant. All right. How would I calculate the rate constant? Just plug in one of the experiments, yeah, with the actual concentrations and the actual calculated rate to get the rate constant K. Does it matter which one you do? No. So if you do experiment 1, your friend does experiment 2, you should get the same K as long as you got the correct order, the correct rate law. If you did not get the correct rate law, then you will not get the correct value for K. Okay. All right. All right, I'll do one more. Yeah. A percent ionization question. Yeah. Can I just make one up? Okay. All right, so what's that? If I put that in water, what will the pH be? H implies it's acid, yes. So its pH should be acidic. But to even make it more obvious, I'll say HC, its Ka is 1 times 10 to the negative 4. Loop. Okay. All right. So HZ is the acid. It's a weak acid because it has a Ka value. So when this dissolves in water, you only get some H plus cations, and that's what contributes to your pH. And you get some Z minus cations, right? Right. So percent ionization depends on how much this reaction goes forward. So essentially, your percent ionization depends on how much Z minus or H plus that you make. So let's make up a concentration. Let's say you start with 0.3 molarity of HZ. All right. And I'm asking you what's the pH, what's the percent ionization. Both of these you can calculate with all this information. So if I have a bottle that says HZ 0.3 molarity, what's the pH? We do our ice table where initial is 0.3. The change line depends on the stoichiometry. So it's minus X plus X plus X. So at equilibrium, I will ionize some of my HZ. So 0.3 minus X, X amount of H plus, X amount of Z minus. So Ka equals H plus times Z minus times Hz at equilibrium. So if I plug in my E line into my Ka expression, I get x squared over 0.3 minus x equals 1 times 10 to the negative 4. That's a quadratic. Do you want to do a quadratic on the exam? No. So what are you going to do to get rid of it? Yeah, going to neglect that x on the bottom. And the reason I can do that is because Ka is small and 0.3 is a big number. X is going to be really small. So if I subtract a small number from 0.3, that number is not going to change that much. All right, so you solve this, x is equal to 1e negative 4 times 0.3 square root. I get x is equal to 0.00548 molarity. What is that the concentration of? It's H plus, yes. So I can get pH by just taking the negative log of that. And so my pH is 2.26. All right, so now the question is, well, how do you get percent ionization? It is equal to the amount of H plus that you have at equilibrium over how much acid you started with initially. So essentially, it's, if you think about this, all right, this is what percent ionization is. It's whatever this X is, it's how much you lose. So it's this number over this number, right? Because we said H plus is X, right? So it's how much this HZ actually dissociates, and that's what percent ionization is. And so we see that this value is that X value we calculated, so 0.005 whatever, 58 over 0.3, so 0.0054, 8.3. We get our percent ionization. Percent ionization is something like 1.8%. So only a little bit of this acid actually ionizes. Okay, so yeah, percent ionization is just related to that. All right, okay, good luck everybody. If you're in my class and you want to sign the thing, I have it up here if you didn't get to sign it.